Hello. In this podcast, we're going to study angled projectile motion. We're going to look at some fundamental concepts and then study key relationships and how to analyze a couple different situations. One, when the landing height is the same as the launch height, when the landing height is higher than the launch height, and we're also going to learn how to analyze when the landing height is below the launch height. Let's take a look at the fundamental concepts. We have an object launched at an angle, so it's not launched perfectly vertically or perfectly horizontally. In this case, this one's launched at a 60-degree angle with an initial velocity, and we get this parabolic path that has a peak height, which is the maximum vertical displacement, and it has a range, which is the total horizontal distance it travels before it lands. As in all projectile motion, the horizontal component of the motion is constant velocity and the horizontal acceleration is 0. The vertical motion is free fall, and on Earth that means that the acceleration vertically is negative 9.8 meters per second squared. And when an object is launched at an angle, the initial velocity in the vertical dimension is not 0. So this is different than horizontally launched projectiles. So let's follow along with this launch. The projectile is launched with an initial velocity, v sub I, and a launch angle theta. Now we can break that into its horizontal initial velocity, v sub ix, and its vertical initial velocity, v sub iy. The launch height and initial vertical velocity determine the time the projectile is in the air, and the initial horizontal velocity and time in the air determine the range of the projectile. Let's look at some key relationships when we're launching a projectile upward. So we start with our initial velocity and our launch angle, and of course that can be broken into the x and y components. And to calculate the x component, we take the initial velocity and we go to our unit circle and multiply it by the x ratio for the given angle theta. For those of you using trigonometry, instead of the unit circle, we're going to calculate that x ratio by taking the cosine of theta. And for the vertical component, we're going to take the total initial velocity and multiply it by the y ratio from the unit circle. And if you're using trigonometry, that is going to be the sine of theta. Next, if we take a look at the range is going to be equal to the initial horizontal velocity times the total time in the air. The total time in the air can be calculated by negative 2 times the initial vertical velocity divided by the vertical acceleration. To calculate the peak height, we use equation 2 using the vertical acceleration and the initial vertical velocity, and for delta t, we use the time it takes to get to the peak, and we can calculate the time it takes to the peak by taking the negative of the initial vertical velocity and dividing it by the vertical acceleration. And notice the time to the peak is equal to 1/2 the total time. Similarly, the horizontal distance to the peak is exactly half the total distance or range the projectile travels. When the projectile lands, the angle at which it lands is going to be equal to the angle at which it was launched. The final vertical velocity when the object lands is going to be equal to the initial vertical velocity, but in the opposite direction. The horizontal final velocity is going to be equal to the initial horizontal velocity because, again, horizontal motion is constant velocity. Our total final velocity is going to be equal to our initial final velocity, but it'll be heading in a different direction. Let's look at a process for quantitatively analyzing angled projectile motion. First, we must use the kinematic equations to analyze each dimension separately. We cannot mix vertical and horizontal quantities. The first step in the process is to calculate the vertical and horizontal components of the initial velocity. So you'll either be using the unit circle or you'll be using trigonometry to do this. Second, we want to list the motion quantities we know for the horizontal dimension. Then we want to list the motion quantities we know for the vertical dimension, followed by determining the amount of time the projectile is in the air. We analyze the vertical dimension if the problem gives us the height. However, we analyze the horizontal dimension if we're given the range, which is the horizontal displacement. Finally, we calculate the distance we were asked to find in the problem. Let's take a look at an example here where the launch height and the landing height are the same. So the Buckskins kick off to start the football game. Our kicker launches the ball at a 30-degree angle with an initial velocity of 20 meters per second. That's about 45 miles per hour. How far did the ball travel before it hit the ground? Step 1, we want to find the component velocities. So we go to our unit circle, or we use our trigonometry, and we find the initial horizontal velocity is 17.4 meters per second, and the initial vertical velocity is 10.0 meters per second. Next, we need to list the quantities we know. Horizontally, we know the initial velocity and we know the acceleration is 0. Vertically, we know the initial velocity is 10 meters per second. We know the acceleration is negative 9.8 meters per second squared. And we know that the final velocity in the vertical dimension is negative 10 meters per second. Next, we need to determine how long the ball is in the air. And to do that, we're going to take equation 1 and analyze it using the vertical motion quantities. We have to rearrange it to find delta t, and we plug in our final and initial velocities divided by the acceleration, and we find out that the football was in the air for 2.04 seconds. And lastly, we need to determine how far the ball traveled. We use equation 2 with our horizontal motion data, remembering that the acceleration horizontally is 0 meters per second squared, so this term goes to 0. We take our initial horizontal velocity, 17.4 meters per second, multiply it by the time the ball was in the air, and we wind up with 34.8 meters for the range of this kickoff. That's about 38 yards. Let's move on and look at key relationships when a projectile is launched downward. As with all projectile motion, the horizontal motion is constant velocity and the vertical dimension motion is free fall with an initial velocity. We can calculate our horizontal initial velocity just like we did before, and the same with our initial vertical velocity. The vertical displacement is going to be equal to the launch height, but in the negative direction. Our total horizontal displacement, also known as the range, is once again going to be determined by the amount of time the projectile is in the air and how fast the object is moving in the horizontal dimension. The peak height is equal to the launch height because the object never goes up. It's always going down, so the highest point is when it's first launched. The launch angle is negative, in this case negative 30. So to find the angle on the unit circle, you need to add the negative angle to 360 degrees. For example, in this case, theta for the unit circle would be 360 degrees plus negative 30 degrees, or 330 degrees. If you're using trigonometry, you can either use negative 30 degrees or you can use positive 330 degrees. To find the total time the projectile is in the air, you need to use equation 2 instead of equation 1 like we did in the last example. Since the initial velocity is not 0, we need to rearrange this equation 2 into the quadratic equation and solve it using the quadratic formula. We're going to cover how to do this in just a minute or two. Moving on from downward launches, let's go back and look at upward launches, only this time the landing height is above the launch height, as in this example. So once again, we have our initial velocity, which we can break into our horizontal and vertical components, and we have our initial launch angle. We have our total displacement here. Our total vertical displacement is delta y, and it is positive. We have our peak height, and to calculate our peak height, we can use equation 2. Just like before, remembering to use our vertical motion quantities and the elapsed time to the peak. And we can find the elapsed time to the peak just as we did before using this equation. The range is again determined by how fast the object is moving horizontally times the total time in the air. To find the total time in the air, we need to use equation 2, and again, since the initial velocity is not 0, we need to solve using the quadratic formula. So let's take a look at a problem showing how we do this. The score is tied with 3 seconds to play as the Buckskins line up to kick a 30-meter field goal. That's about 33 yards. We win the game if we make it. The ball is kicked at a 45-degree angle at an initial velocity of 20 meters per second. Did the ball clear the crossbar? Now here's the hint. The crossbar for the goalpost is 10 feet above the ground, which is about 3.3 meters. So we need to find out how far the ball has traveled horizontally when it is still 3.3 meters above the ground. So let's follow our process. First, we want to find the component velocities. So we go to our unit circle or our trig functions and we use an angle theta of 45 degrees and we find out our horizontal and vertical components. Then we list what we know. Next, we want to determine how long it's in the air. We're going to use equation 2 for that. We have to just plug in the numbers. We need to rearrange it to look like the quadratic equation. So I'm going to subtract 3.3 from both sides of this equation, and that'll give me 0 on the left-hand side, and on the right-hand side I have this expression. Now what I did is I went ahead and I took 1/2 times negative 9.8, and that gave me negative 4.9. And I dropped the units just so we didn't take up as much space. Notice this is in our quadratic equation format. In math class we learned that a quadratic equation was 0 equals to a coefficient a times x squared plus a coefficient b times x plus a coefficient c. So notice in our physics equation, delta t squared is the same as x squared, delta t is the same as x, and negative 4.9 is the same as a, 14.2 is the same as b, and negative 3.3 is the same as c. So we can use our quadratic formula, and wherever we have a b, we're going to plug in 14.2. Wherever we have an a, we're going to plug in negative 4.9. And where we have the c, we're going to plug in negative 3.3. Our two answers are 0.25 seconds and 2.6 seconds. So both of these are mathematically correct, but let's look at what's going on physically. 0.25 seconds is just after the ball was kicked, and so the ball is 3.3 meters above the ground at that time, but it's on its way up, and that's not what we're interested in. We're interested when the ball's on its way down and 3.3 meters above the ground, and that's the 2.6 seconds. So we do not want to use the 0.25, we want to use the 2.6 seconds. So then finally we go on and we determine how far it traveled using equation 2 and remembering that the acceleration horizontally is 0, so that first term goes away, and we multiply our horizontal velocity, 14.2 meters per second, times the time in the air, 2.6 seconds, and we find that the ball traveled 36.9 meters by the time it reached the height of the crossbar, 3.3 meters above the ground. And of course at that point it's already beyond the crossbar, and yay, we won! Let's take a look at the other situation, and that's where the projectile lands below the launch height. Notice that as we follow the path of the projectile, there is a symmetry in its path until it reaches the launch height, and then that's where the symmetry ends. But for this first part, the downward journey looks just like the upward journey, but we lose the symmetry once we fall below the original launch height. That means that some of the relationships that exist when the launch height and the landing height are the same do not exist when the landing height is either above or below the launch height. The peak vertical displacement, we still use equation 2 with our vertical motion quantities. However, notice the peak displacement is not measured from the ground, it's measured from the launch height. So that's different than when the launch and landing height are the same. Our time to the peak is the same as before. Our total vertical displacement is equal to the launch height, but in the opposite direction, the negative direction. And so to find how far the projectile is above the ground, we have to take our peak displacement and add it to our total displacement, and that'll give the distance from the ground to the highest point in the path of the projectile. Calculating the horizontal range is the same as before. To find the total time in the air, we're going to use equation 2 but we're going to have to once again use the quadratic formula to solve it. Let's take a look at an example where the landing height is lower than the launch height. Tiger Woods is hitting a tee shot at a par 3 hole. He wants to land the ball close to the hole, which is 150 meters away. Where he's teeing off from is 5 meters higher than the hole and the green. He launches the golf ball at a 60-degree angle with a velocity of 40 meters per second. How close will the ball be to the hole, assuming it rolls 3 meters after it first hits the green? Our first step is to find the component velocities. We're going to use 60 degrees as our angle for our unit circle or our trig functions, and we find out that the initial horizontal velocity is 20 meters per second and the initial vertical velocity is 34.8 meters per second. Next, we list the horizontal and vertical motion quantities that we know, so we've gone ahead and done that. Then we need to determine how long it's in the air. We're going to use equation 2, and we have to go ahead and just plug in our values, and then we have to rearrange it to get into our quadratic equation format. And so to do that, I'm going to add 5 meters to both sides, and that leaves us with this format. We set up our quadratic formula, and wherever there's a b, I'm going to put in 34.8. Wherever there's an a, I'm going to put in 4.9, and for the c, I'm going to put in 5. Our two mathematically correct answers are negative 0.4 seconds and 7.2 seconds. Obviously, we can't go back in time, so while negative 0.14 is a correct mathematical solution, it's not physically possible. This ball was in the air 7.2 seconds. Now we can determine how far the ball traveled, so we use equation 2, remembering that when we use the horizontal dimension in equation 2, acceleration is 0, and so we get the distance the ball traveled before landing was 144 meters. Remember, it's going to roll another 3 meters, so it's 147 meters when it stops rolling, and that's only 3 meters or about 10 feet from the hole. Good shot, Tiger. This wraps up what we wanted to cover in angled projectile motion, so let's summarize what we learned. First, angled projectiles can be launched upward or downward. The landing height can be the same as, lower than, or higher than the launch height. The upward and downward portions of the projectile's path are symmetrical when and only when the landing height and launch height are the same. The kinematic equations are used to analyze the vertical and horizontal dimensions separately, just like in other projectile motion. The horizontal motion is constant velocity. The vertical motion is free fall. The initial vertical velocity and the vertical displacement determine how long the projectile is in the air, and the initial horizontal velocity and time the projectile is in the air determine how far the projectile travels horizontally. I hope you found this information helpful, and have a good day.